Welcome to Eazy Btech, your guide for Btech and beyond. My name is B. Manohar, working as an assistant professor. I'm interested in a subject electronic devices and circuits, and the topic is semiconductor physics. Students, we have vast applications in electronics, in telecommunications and in signal processing. Electronic devices are widely used. Okay. We start semiconductors. Types of semiconductors. The today's topic is types of semiconductors. Types of semiconductors. Okay, in the previous session we have discussed what is a semiconductor, how the semiconductor energy band gaps are there, and how the silicon and germanium energy band gaps are decreases. Now you can see these semiconductors are classified two types: intrinsic semiconductor and intrinsic, and the second one is extrinsic semiconductor. Extrinsic semiconductor. This is an extrinsic semiconductor. These all are known as indirect band gap semiconductor. Indirect band gap. And second one is direct band gap semiconductor. Direct band gap semiconductor. Okay, semiconductors are classified two types. One is an indirect band gap semiconductor. Another one is a direct band gap semiconductor. In an indirect band gap semiconductors, again we have intrinsic and extrinsic semiconductors. Okay, we will discuss what is an indirect band gap semiconductors. Indirect. Indirect band gap semiconductors is nothing but examples of indirect band gap semiconductors are silicon and germanium. These two elements are known as indirect band gap semiconductors. In an indirect band gap semiconductors, both we will say this is a conduction band and it is a valency band. Okay, this is we will call as a conduction band and this is we will call as a valency band. Now this is we will call as a forbidden gap. Forbidden gap. Okay, when an external field is applied, the electron from the valency band reaches to the conduction band. After lifetime of electron in the conduction band, the electron falls back to the valency band. Now the returning path of an electron is not in a straight path. It has a random manner. The path of a random path. Path of electron is a random path. We know this. This we will call as minima, and this we will call as maxima. Okay students, you can clearly understand here. This is a valency band. What is a valency band? In the first lecture we have listened. Valency band is nothing but it is a filled band. The electrons presented in the valency ball will possess a strong electric field or a strong energy, because the electrons are very closest to the nucleus, which having a strong energy. And upper band we will call as a conduction band. The electrons presented in this conduction band will having a weaker energy, because the electrons presented in conduction band, they are some far away to the nucleus. That is why they are loosely bounded. That is why they are known as a unbounded electrons. The electron presented in the conduction band, we will call it as a bounded electrons, which are having stronger energy. The conductivity of semiconductor, when an electron from valency band to conduction band reaches, then electrical character, the conductivity of semiconductor can exist. Otherwise it falls under the category of insulator. If an electron from valency band moves into the conduction band, then the conductivity can take place. Now it depends upon this energy band gap, that is a forbidden gap. Forbidden gap of a semiconductor is 1 electron volts. Now in this indirect band gap, the returning path of the electron is in a random path, not in a straight path. Now if you see in the direct band gap from the EKY diagram, this we will call as a conduction band, this we will call as a valency band, this we will call as a maxima of conduction band, valency band, and this is minima of conduction band. This is maxima of valency band and it is a minima of conduction band. Now when an external voltage is applied, electron from the valency band reaches to the conduction band. After its lifetime, the electrons from the valency band, the electrons from the conduction band can move into the okay. After its lifetime, the electrons in the conduction band moves in a straight path. Means the traveling path of the electron is a straight path from the conduction band of minima to valency band of maxima. The path traveling in a straight path. When an electrons are falling from conduction band to valency band, it start radiating energy. Examples of these direct band gaps are gallium arsenide, gallium phosphate, indium phosphate, gallium arsenic phosphate. Now you can see this we will call as a compound semiconductor. This we will call as a compound semiconductors. What is a compound semiconductor? Gallium belongs to third group, arsenic belongs to fifth group. Now third and fifth group combination takes place. Here gallium is third group, phosphorus is fifth group. Now such type of, this is a two types and it is a binary compound semiconductor, it is a trinary compound semiconductors. Okay students, I hope you understood. In a direct band gap semiconductors, the traveling path of electron from conduction band to valency band is in a straight path, whereas in the case of indirect band gap semiconductor, the traveling path of electrons is in a random path. Now we discuss clearly what are the indirect band gap. Indirect band gap. There are intrinsic semiconductor and extrinsic semiconductor. Now, if you take intrinsic semiconductor, in an intrinsic semiconductor, we can call these are pure form of semiconductor. It is a pure semiconductor which are belong to fourth group elements. These are the fourth group elements. Those are carbon, silicon, germanium, phosphorus and tin. This lead and tin. Now here carbon has an insulator property. Silicon and germanium belongs to the fourth group element which can act as a pure semiconductor. The pure semiconductors are silicon and germanium from the tetravalent or from the fourth group elements. Okay. Now, how many valency electrons in these have 4 valency electrons. Number of valency electrons presented in an pure semiconductors are 4 valency electrons for silicon and germanium. This we will see from this electronic configuration. Suppose take a silicon energy band gap is atomic number is 14. We will write we have the cells like S cell, we are having 2 cells. P cell we are having 6 electrons. D cell we are having 10 electrons. And F cell we are having 14 electrons. Now, as per the atomic number, this electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p2. Students, you can clearly see here. The first, you are having 2 electrons. In the first orbit, you are having only one S cell, only which has 2 electrons. In the second cell, you are having S and P, total 8 electrons. In the third, you are having SPD, but as per our atomic number for a silicon, it has only 2 in 3s2 and 3p2. In S orbit, 2 electrons and p2. Total in its outermost orbit. Third cell is its outermost orbit. In its outermost orbit, it has 4 electrons. That is why it falls under the category of fourth group element. Silicon has 4 valency electrons. Similarly, if you take a germanium, germanium atomic number is 32. It has 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. Now if you count here, you are having 4, In third cell you are having 18. In second cell you are having 8 and first cell 2. 2 plus 8 10. 10 plus 18 28. 28 plus 4 32. Okay, in its outermost cell is fourth cell, which has 4 valency electron. Okay. Carbon doesn't have a semiconductor property. Silicon and germanium are the pure semiconductors, whereas lead and tin belongs to the fourth group, but they can act as a conductors. Now you can see in an intrinsic semiconductor, it is a pure semiconductor. If you take a silicon, the covalent bond structure in an intrinsic semiconductors are like this. See here, this is a covalent bond structure. Now you can see here, silicon with a 4 valency electrons. All silicon atom has 4 valency electrons. Now you can see sharing of electrons between the two atoms are known as covalent bond. Now you can see, now this and this silicon atom are sharing of electrons. This we will call as a covalent bond, which is a strong bond. Okay, now you can see in the structure, silicon covalent bond structure it is. Now you can say all these completely pair, this covalent bond, this covalent bond, this covalent bond, this all band is completely filled. Now 4 of the 4 electrons, now these 4 electrons and these 4 electrons are completely bounded. That is why the electrons in the intrinsic semiconductor, electrons in the intrinsic semiconductors are known as bounded electrons. Bounded electrons. Electrons in an intrinsic semiconductor are known as bounded electrons. The energy is very strong, even though if you apply some external field, at 0 degrees Kelvin, if you apply some external field, this covalent bond cannot be breakable. And there is no movement of an electron, never moves into the free band or free space. This is a forbidden gap or free space. Now no electron can become a free electron, and conductivity is not possible in an intrinsic semiconductor at 0 degrees Kelvin. Okay students, I hope you understood. At 0 degrees Kelvin, due to a strong covalent bond exists, This semiconductor structure of a covalent bond can act as a insulator or a bounded electrons within the covalent bond. That is why this intrinsic semiconductor at 0 degrees Kelvin can act as a insulators. But the conductivity of intrinsic semiconductor can exist at a various temperature. That is, at 300 Kelvin at room temperature, what happens? Due to this temperature increase, what happens? Due to temperature increase, this covalent bond whatever the covalent bond is there, this covalent bond can break up, and this electron can become a free electron. This electron presented in the covalent bond can become a free electron. Due to these free electrons, it starts a conductivity. Okay. The students, you can remember the point here. In intrinsic semiconductor, at 0 degrees Kelvin, it can act as insulator due to strongly bounded electrons in the covalent bond. Okay. As temperature increases, that is at 300 degrees Kelvin, covalent bond will break. Covalent bond breaks. Electrons are becoming free electron, which leads for conductivity. The electrons at 300 degrees Kelvin in an intrinsic semiconductor are known as unbounded electrons. Okay, students, you understood about intrinsic semiconductor. Next, extrinsic semiconductor. Extrinsic semiconductors. Extrinsic semiconductors are known as impure semiconductor. Impurity is added to pure semiconductor to form p-type and n-type elements. Okay. Now, when see here, third group boron, aluminium, gallium, and the fourth group elements are carbon doesn't have the semiconductor property. we are using is silicon and germanium, and fifth groups are phosphorus, arsenic, antimony. You have nitrogen and bismuth. They are not used in the construction of n-type. Okay. When boron impurity is added to pure semiconductor, that is either silicon or germanium, then formation of semiconductor is known as p-type. Okay. The doping concentration you can see, when one boron impurity is added to 10 power 3, then we will call it is a heavily doped. One impurity atom for 10 power 6 to 8, this is known as moderate doped. When one impurity for 10 power 8 to 11 is known as lightly doped. Now the doping material, 1 part in 10 power 3 heavily doped, moderate doped, lightly doped. Now when one boron atom for the formation of a p-type semiconductor, one boron impurity added to 10 power 3, it is a heavily doped, and for this the examples of tunnel diode. Tunnel diode is an example for a heavily doped material. For a moderate doped material, we will write Zener diode. One boron impurity added to for this structure, and one impurity atom 10 power 8 to 11. This we will call is an ordinary diode, that is PN junction diode. This is PN junction diode. This is a types of doping level of the semiconductor. Similarly, if you take n-type material, for an n-type material, when fifth group element or fifth group impurity atom, fifth group impurity atom is added to pure semiconductor, then formation of semiconductor is known as n-type semiconductor. Okay students, today we will conclude it. This is a p-type and n-type semiconductors. Welcome to Eazy Btech, guide for Btech and beyond.